As I mentioned in the last clip, an agreement on what is known and what is unknown can lead two people to the same probabilities. The example there was dice where symmetry was used, see clip 7. Something similar happens in statistical mechanics, which was developed in the 19th century. At that time, it was known that matter was composed of atoms and that each atom could be, at least approximately, calculated using Newton's laws. But calculating what happens with a large collection of atoms, such as an atmospheric model, an expanding gas in a turbine, or an iron rod radiating heat to a thermal bath, would be a hopeless task even if the state of each atom, the so-called microstates, were known. Which it of course will not be. What was of interest anyhow was not to predict the next microstate, but rather to predict large-scale properties like temperature or pressure, based on other large-scale quantities like energy or volume. What they envisioned then was a collection of possible microstates that yielded the same energy and volume, for instance, and then say, this is all we want to condition on with regards to the microstates. This is our common knowledge. These collections of microstates, called ensembles, were then used for gaining a probability distribution for the rest of the large-scale properties. And usually these properties tend to be rather sharply defined around an expectation value. And they could identify collections of properties conditioned on knowledge about quantities of interest, which is why these collections have names like the canonical ensemble and the grand canonical ensemble. Similarly, we can describe common knowledge of interest for such things as specific measurement errors or the throwing of dice. However, identifying common knowledge of interest for determining the probability of life on various heavenly bodies must be extremely difficult. It's also worth noting that if you got an agile imagination, you can think of Bayesian probabilities in a semi-frequentist way. For instance, let's say you're playing cards and each are dealt 7 cards. You haven't got the queen of spades, and you are wondering if the person to your left has it. Well, then you can imagine a large set of repeated dealings and look only at those dealings that are resulted in you not getting the queen of spades. You can then look at the expected rates of times when the person to your left got it and call that a probability. Note that this is a subjective probability. The person to your left knows whether he or she has the queen of spades or not. Also note that you could call the probability arrived at objective in the weak sense, in that everyone willing to do the necessary calculations and capable of doing them correctly would agree on what probability you should apply. Even a person to your left who knows whether he/she has the queen of spades or not could agree on this. If you've got an incredibly agile imagination, you can even imagine drawing the universe again and again and conditioned on the universes which has you knowing the same things, in order to evaluate, for instance, the probability of life on Mars. It seems that Daniel Dennett can do this, and if you also can, then good for you. But with a truly Bayesian outlook on the probabilities, you don't need this, and you don't have to obsess about what is and isn't random. What matters is what you know and what is presently unknown, but linked to what you know. It should also be noted that there is one aspect of the physical world that does seem to be truly random, in the strong sense, namely quantum physics. According to the Copenhagen interpretation, you can have exactly the same quantum state and get different results each time you measure. This is often called the collapse of the wave function, and the probability calculation is one of the laws. This isn't a real problem for Bayesians. A truly objective probability, if it exists, would also represent the best subjective probability achievable. If nature doesn't know what happens next, but has a probability distribution for it, then this is the best we can do too. Still, some people have had problems accepting the randomness of quantum theory and propose that the uncertainties come about because we are uncertain about so-called hidden variables of the quantum systems. But such theories have been largely discredited because of the bad properties they necessarily possess. Then there's the decoherence and or many-world interpretations, where probabilities are not part of the laws, but are at least assumed to pop up as a result of the rest of the laws, which are deterministic. Roughly stated, the waveform never collapses, rather the rest of the world becomes connected to the quantum state of the particle and splits into the number of possible outcomes. If the probabilities then can be called real or not in this scenario is, I think, a matter of taste. As I said, as a Bayesian, I fortunately don't have to obsess about this.